Welcome again. So we'll be discussing transient solutions, transient analysis, where the solutions depend on time. That's really what we're discussing. In the previous lecture, what we learned is how to discretize the spatial domain using finite elements, and then we learned how to march the solution, find the solution as a function of time by discretizing the time domain using time integration. And I taught you a Newmark beta procedure in how to do that procedure. Okay. So with that said, let me play a video here that shows the Tacoma Narrows bridge collapse. It's a little bit lengthy. Going back and forth. All right, so what's going on there? So what is really going on there is that every structure has a dynamic characteristic. And that structure is going to be comprised of fundamental modes of the structure, okay? In this particular case, the bridge design had some fundamental behavior, dynamic behavior, that cause excitation of that behavior upon introducing an external forcing function. And probably what happened there was that the forcing function applied, maybe from the winds, that forcing function, its frequency probably matched the frequencies of that bridge in some way. Okay? So in the previous lecture, what we saw is a time discretization using time integration. But we didn't really learn much about the dynamic behavior of that beam. Do you agree? All we did was to apply a load, instantaneous in one case. In another case, I applied it slowly. In another case, I applied a deflection and let it go, right? But we didn't really study the dynamic behavior of that beam or that bar, right? And so what we really want to do when we're looking at dynamic problems is not just to close your eyes and run the analysis to see what you'll get, but what we want to do is to really understand the fundamental behavior of the structure, okay, in terms of its dynamic characteristics. Because if we understand that, we can then use that to our advantage in design, or we can actually use other techniques to actually find a solution in a much computationally efficient way. Only if it's a linear system, okay? And I'll be discussing some of that today. So the topic for today is modal dynamic analysis. Again, it's a special topic because it's not really included in this lecture, in this course, but we're adding this because I think it's beneficial to your career to learn these things. So we learned that in the transient dynamic analysis with direct time integration, what we covered last week, is that what we did there, we discretized the spatial domain using finite elements, and then we integrated the equations of motion using the loading history information and using the procedure called Newmark beta method. In that case, what we did, we solved for nodal displacements, and if I have displacements, do you agree I have velocities? Right, because I know how displacement changes over time, so then I know how velocities change over time, and I know accelerations, how they change over time. Not only that, if I know the displacements, do I know the strains? If I know the strains, I know how the strains vary over time. And if I know how the strains vary over time, do I know how the stresses vary over time? And I do know that through Hooke's law, and we've learned that. Okay. So what are the benefits of this approach? the benefit is that you can predict the structural behavior due to a time varying excitation. The way we did it, you can predict that behavior very well. It works for nonlinear problems, contact problems, plasticity, and so forth. It allows applying forces and enforcing motions. You can also explicitly define the transient load as an explicit function of time. So I can say, hey, you know, this forcing function, excitation, behaves this way as a function of time. I can explicitly put that formula in. But if I wanted to tackle a million degree of freedom system from a dynamic standpoint and solve these equations, we will need to solve these millions of degrees of freedom not only once, like you do in a static problem, but we're going to have to solve it for every single time increment, every 1e minus 5, like what we did last week. Well, that's computationally expensive because I have to do that over its time, complete time domain. So in a launch vehicle, maybe you have to solve it every, for 3 minutes, maybe every 50 hertz, 100 hertz. Or if I have another application, I may have to solve this time domain problem over a long period of time. And so using the transient dynamic analysis approach we discussed last week may not be computationally efficient. Okay? In some problems it is efficient, but in many problems it may not be efficient. Okay? And so if you have a linear system, then maybe we can take advantage of this technique we'll be talking about, which is learning about the dynamic characteristics of the structure and taking that to our advantage and applying those concepts to maybe have a more efficient approach at solving these problems. Is there a question in what I've discussed? Okay, so a dynamic analysis that entails looking at the frequency and modal analysis response of a structure. You have various things you can do. You can determine the free vibration eigenvalue problem. I'll discuss that. You can determine the natural frequencies and the normal modes, the mode shapes of that structure. So every structure has fundamental dynamic characteristics that are comprised of mode shapes and frequencies. We can then use these normal mode shapes, these shapes, and these natural frequencies. We can use this DNA, this information about the structure, and use it to solve a transient problem by using these modes. Okay? A structure, like for example, the table you're sitting on right now, that table has infinite number of mode shapes and frequencies. But not all modes and frequencies will be relevant. For example, you don't see your table vibrating, with a bunch of, it's not undulating, right, from left to right dramatically, right? Most likely, if anything, you guys are putting your weight on that table, so it's kind of bending just one way, right? So in that particular situation, maybe me including mode shapes that are not relevant to the problem is an overkill. Okay? So if we learn the dynamic characteristics of the structure, we can use that to our advantage. So what is the motivation of analyzing free vibration problems? You can verify stiffness requirements. That's one possibility. You can take your model that has dynamic characteristics, and we'll talk about that, and compare it to reality. Does my model compare well to reality? We can determine the dynamic characteristics of the actual structure by measuring the modes and the frequencies and comparing that to your finite element model to see if they make sense, one against the other. We can assess whether there's a dynamic interaction between one component to another component. So for example, I could have a resonant condition where one component is vibrating, but it causes another component to vibrate excessively. I could also look at evaluating design changes. So maybe I want to prevent exceeding a particular frequency of concern. then I want to stay away from that frequency range, and I will have to design my structure to allow for that. We can also use free vibration problems to analyze transient response, and that's a lot of what we'll be talking about. We can also look at designing the structure so its frequencies maybe are far removed from the frequencies, the excitation frequencies. Because if the excitation frequencies I put into the structure coincide with the frequencies that the dynamic characteristics of the structure that you're looking at, if they coincide, you can have a resonant condition. Don't you agree? We can also use it for damage detection. Say that I have a wing, and that wing has particular mode shapes and frequencies. If I induce damage there now to that wing, due to maybe something happened to that wing that's damaged now, and now I calculate the mode and frequencies of that wing, well, maybe the modes and frequencies of that wing will now be different because there's damage. And so that could tell us, hey, there is potential damage in the structure that I did not expect from the ideal situation, for the ideal construction, manufacturing. Okay? And so, you know, some of those techniques are discussed in a lot of different arenas, including structural health monitoring. How can we monitor the structure in real life? By gathering accelerometer data from real structures. So then when they're in service, the structures are in service, if there is damage occurring in the structures, I can take that signature and I can process that signature to study its dynamic characteristics. And if the dynamic characteristics are showing that perhaps they have changed over time, and maybe it's because the stiffness is decreasing. Don't you agree that if there's damage, stiffness most likely will soften, will change? Does that make sense to you? Like if I damage a beam, doesn't its stiffness kind of get reduced? So if that shows us a stiffness reduction, well, perhaps I will see that in the mode shapes, in the frequency information, and I can use that to then determine, hey, there was indeed damage to that structure. So this free vibration dynamic characteristics problem that we'll be looking at today is fundamentals to finite elements in many different ways and into real applications. If we look at a simply supported plate, you know, for example, a real structure that's not discretized is going to have infinite number of eigenvalues and mode shapes. It can take infinite number of mode shapes. Some of them will be more fundamental than others. So for example, for a simply supported plate, the fundamental mode shape for this plate is just simply is bowing out in one direction. Okay? And so now I know that's the fundamental shape. Maybe in a different, as I increase the mode shapes, perhaps I will have different modes that are occurring in that structure. They're part of that DNA of that structure, dynamically speaking. And as I increase the number of modes and I look at higher modes, you're going to see more and more oscillations in that structure. Those are present, inherent to the structure. That depend, the frequency of motions depend on the geometry, the material. It depends on the boundary conditions of the problem. And these things together define that DNA that we're talking about. That will then basically either excite particular modes during an actual application, or it could be that the structure is bending back and forth due to a combination of these modes. Can you imagine that for a linear system, that the deformation of a system is basically comprised of a combination of these guys? You follow me? So for example, I could have a situation where a plate could be bending in a way that comprises of the summation of this mode and maybe this other mode. Okay? Yeah? You follow like the concept? So the dynamic behavior perhaps can be described by the addition of any of these modes, or the addition of all these modes. Okay? Maybe some of them contribute more than others. Okay? For a particular application, we may see, for example, that Tacoma Bridge that you saw, indeed, it had probably infinite number of modes, right? Yeah? I mean, it is. It will have infinite number of modes. But did you just, in that video, I think you saw that there was a particular mode that kept showing up in that video, right? Now, we don't know if it was a single mode or was a summation of multiple modes, but it was not infinite number of modes showing up. You could see that that bridge was swaying in a particular manner, okay? And so, again, mode shapes and frequencies form the DNA of that structure from a dynamic standpoint. So let's look at a little bit more theoretically here, because we need to understand a little bit better where this came from, this dynamic eigenmodes and frequencies come from. So if we know the equations of motion, you agree we have the equations of motion, we know them, right? And if I have no forces here, so let's say I have no forces applied, no natural boundary conditions applied, no distributed forces applied, we will call that a free vibration problem, in essence, because I don't have a load applied at this point in time. And so if I now assume a harmonic solution for the deflection, and I assume it to be in this manner, W equals capital W, which depends on x alone, to the EI omega t, and I were to substitute this in here, what you will find is that I'll have a number of derivatives on EI omega t, so twice derivatives on EI omega t, and I got I squared minus 1, I squared, which is minus 1, that's why you see that's minus 1, and the omega squared is from the second derivative of EI omega t, which comes from this here. And then this one does not depend, this is not a derivative with respect to time, but W here is a function of Wx EI omega t. So EI omega t, I'm not taking derivative of that, so that's why it's just a factor there. And now, this is true for any EI omega t, so I can factor that out, because EI omega t cannot be 0. And when I factor that out, I get this equation here, that equation. And let me call, for the sake of convenience, let me call this coefficient here lambda equals omega squared rho a EI 1 to the 4th. So I'll make that substitution there. It's more for convenience, okay? And what we notice in this particular situation is that I have 0 here, this is a function of x, and that's all I have. What I can do now is assume, and this is all now going back to your differential equation class, but just to remind you, what you will have done there is you will have assumed the displacement of a particular form, okay? And what you will have done, do you remember this a little bit? Yeah? You'll take a displacement of this particular form, and of course, nowadays you plug this into Mathematica or MATLAB and it'll tell you how to do it. But I think I need to remind you a little bit how this works, so when I go to finite elements, you understand a little bit better what we're talking about. So when I substitute this displacement assumption into this differential equation, and I enforce the boundary conditions of the problem. So it's a cantilever beam, an example we're looking at. It's fixed on the left-hand side. So don't you agree that the deflection and rotations are 0? Yeah? Don't you agree that if it's free, I'm not applying any load on the right-hand side of that cantilever beam, that there's no shear or moment applied. So therefore, W double prime and W triple prime is 0 because there's no shear or moment on the right-hand side. And so now I have a displacement assumption that will substitute in here with 4 boundary conditions. And when I plug that in there, what I get is a 4x4 matrix times a bunch of unknown coefficients that need to be found to solve this differential equation. I mean, this is something you may have covered in differential equation. I'm just reminding you the process that you chose, that we were taught on how to solve for these coefficients. And we realized, well, now what I have is this matrix. They're all knowns. We know that's 0, sine of 0 is 0, cosine of 0 is 1. You can evaluate all these things. And lambda is known. Remember, lambda is known because lambda is omega squared rho A over EI. Now, it's not actually fully known because we don't know what omega is right now. I'll get to that in a moment. But this is what I have. This is what I have. And the situation is simple. What is the trivial solution you see here? Sorry? All these coefficients, all C1, C2, C3, C4 are 0, then this equation is true, right? So that's a trivial solution. But there's another solution that can be found, and that can be found as an eigenvalue problem. So if I find the determinant of this 4x4 matrix, and I found the determinant of that, what I'll get is a fourth order quartic equation, which we call characteristic equation. And from that characteristic equation, when you actually do this home, if you want to go ahead and do that, what you'll get is this equation right here. So the determinant of all this actually just boils down to this equation when you do it. And it turns out that when I find the roots of this equation, what I find is that the lambda L1, so this coefficient here, this value here, are these values for this to be equals to minus 1. Because that's what you find. So, and you find there's infinite of them. You can keep going forever. Which makes sense. We didn't do any discretization. This is a beam. I haven't discretized it. This is what it is. It's a continuous system. So I should have infinite eigenvalues. Okay. And so that's the point I'm trying to make here. So now that I found these lambda L's, since I know lambda L, since I know this value, okay, now I can calculate omega, the frequency. Okay? And so when you do that, you get this formula here. Omega I is lambda L squared of EI rho A L to the fourth. And you guys can now determine the frequency, which is omega divided by 2 pi. So this one is radians per second. We have to convert that to hertz, so it's per second, cycles per second. Okay? So this is what we'll be using as the frequency of the system. Okay? Any questions on that? So it turns out that there is a solution to this problem. That's not just a trivial solution. So the trivial solution gives you the left-hand side equals to the right-hand side, okay, with C1, C2, C3, C4 equals 0. But it turns out there is an alternative solution to this problem, and that solution is given by these eigenvalues, and that allows for you to get the left-hand side to be equal to 0 for non-C1, C2, C3, C4, non-zero values of those. Okay, is that clear? Yeah? Okay, excellent. So it's a continuous system, right? It's a continuous system, and that's my characteristic equation. And there happens to be combinations of lambda L that can come up with that will make this equal to minus 1. And the number of them is infinite. There's infinite number of them. Okay. Remember, these is not finite elements right now. We're talking about continuous system. I haven't done any discretization whatsoever. This is the exact solution. Actually, what you see here is the exact solution to this partial differential equation. That's the exact solution. We haven't done any discretization. Okay. Is that clear?
If you have an infinite number of lambda L's, how do you know which omega is the one you're designing for?
We'll talk about it. We'll cover that. Okay. So now let's see how we will have done the same problem using the weak formularity. Let's see how we will have determined the frequencies, and I'll show you how to determine the mode shapes. I didn't cover that here because that is covered in your differential equation class, but once you get your frequencies, you can plug them back in here, and then you can get the mode shapes of each of these frequencies. So each frequency is going to go with a mode shape. So for each frequency, there'll be one mode shape, and since there's infinite frequencies, right? Eigenfrequencies, how many mode shapes will I have? Infinite number of them. Absolutely. And so I didn't want to go through the process 100% because I don't want to focus on the differential equation aspect. I want to just move to finite elements when it comes to this. So when I look at how to develop the weak form, it's not very different from what we've covered in the past. That's the weak form Galerkin for a beam. You agree? We've covered that. We developed this equation. For a free vibration problem, what I want to do is set the distributed forces to 0, okay? And I want to set all these external forces to 0. I don't want to deal with them right now. So we're looking at free vibration problem. We can only impose essential boundary conditions. That's really all we want to do. Okay? We want to constrain the body. Okay? We don't have to actually. If you don't constrain the body, then you will have some rigid body modes. And maybe we can actually do an example later on with abacus. I don't know if we will get to that, but it will be interesting to remove all the boundary conditions and run it to see what we get, actually. But you should get, rigid body motions. Okay, so when I remove all the forces, I'm left with this equation here, and that is the free vibration problem, the weak form Galerkin. And you can see here I have already weaken the continuity requirements. I don't want to repeat all those steps again because we covered that extensively in your homework and in these lecture notes. What I'm going to do, we're going to plug in the following approximation. I'm going to plug in an approximation for W tilde, which is equal to shape functions, okay, times phi ei omega t. And these phis, what these phis are, they are, remember when I had, this used to be D before? I'm calling it phi, but it's the same. It's basically the deflections of the nodes. So how many degrees of freedom we have for a beam, for Euler-Bernoulli beam? 2 on each node, right? So this vector right here, phi, is going to contain these values, v1, theta 1, v2, theta 2, okay? v1, theta 1 at node 1, v2, theta 2 at second node. Now we could have even more advanced shape functions and more degrees of freedom, like with a middle node. Remember we discussed that you can have a middle node? Well, in that case, I will have 6 values here in that vector. But I'm going to use phi, and it will become apparent why I'm using phi as I move along. Times ei omega t, so I'm going to assume now that the time domain has been replaced by ei omega t. This is a little bit different from what we've done before. Okay? It's different from what we've done in the previous lecture. In the previous lecture, phi was a function of time. In this lecture, phi is basically values. Okay? Values of phi times ei omega t. And ei omega t is the only thing now that's a function of time, while the phis are not changing as a function of time. So that's different from the previous lecture. Please revisit that after this lecture notes, when this lecture concludes. Then I can calculate the second derivative of w, and what I get there is that n is the only thing that's a function of x. You agree? Yeah? Phi is not a function of x or t, and then ei omega t is a function of time. So that derivative just becomes second derivative of n respect to x, second derivative of n respect to x times phi bold. And I'm missing ei omega t there. If you can take a note, I'm missing ei omega t right here. But I should put ei omega t there. And then I have the second derivative of w respect to time. And that one is easy because n does not depend on x, on time. Phi does not depend on time. It's only ei omega t. So that derivative, second derivative of that is just minus omega squared. And so that's what I get. Minus omega squared n bold phi ei omega t. Okay? And again, I will just select v to be the transpose of the shape functions, just like we did before. Okay? So what is the difference? Let me remind you again one more time. What is the difference between this lecture and the previous lecture? In the previous lecture, we assumed that W tilde is n times phi. And phi was a function of time. It looked like that. N was a function of x, and phi was a function of time. Now what we're saying is that WT less n bold, which is a function of x, phi, which is values of v1, theta 1, v2, theta 2, times ei omega t. So I'm decoupling it here and here, while phi it will be values that you'll find and are fixed over time and space. Okay, is that clear? Yeah? All right, so I'm going to go ahead and substitute that into my weak form Galerkin. And when I do that, I'll substitute all these into my weak form Galerkin. And what I find is that E omega t actually factors out. And you're left with this equation here. EI B bold B phi minus omega squared rho A N bold T N bold phi. And again, you will have practice, believe me. I'll make sure you have a good homework. Okay? And then I will take this phi and I can factor it out in this manner. Okay? And I have an omega squared here. Let me contrast this with what we did in the previous lecture on Tuesday. There, what we had was we did not have this omega squared. We did not have phi bold factoring out altogether, right? Because phi bold was a function of time. What we really had was phi bold here, and then we have phi bold double dot here, the acceleration. And that was the phi bold there on Tuesday was a function of time. But again, I made phi bold not a function of time, and what I've really done is assume a harmonic solution, and this E omega t factored out. That's really what happened here. And because E omega t cannot be 0, what I end up with is this equation. Okay, that's what I end up with. And this should have been phi bold. It was an error from my side. So instead of d bold, it's phi bold. Okay, so you have any questions on what I've covered so far? Okay, because I'm excited to show you what will happen next. Because the next step is that I'll calculate the integrals like we did before. Nothing different. We calculate k bold, n bold. Remember we covered that? Yeah? So what if I plug that into my eigenvalue problem? Because in reality, if I have n bold and k bold, what I've done is I evaluated this integral altogether. So that's k. I've evaluated all that as m. So I have k minus omega squared times m. And so what I have now is this eigenvalue problem again. Why I know it's an eigenvalue problem? Because there's a trivial solution to this problem. The trivial solution is v1 equals 0, theta 1 equals 0, v2 equals 0, theta equals 0. If these are 0, what happens? The left-hand side equals the right-hand side, which is 0. But that's a trivial solution. There's also a non-trivial solution, and that can be found by determining what values. Remember, rho A, L are given. You know that, right? Those are given. Do I know EI? I know EI. I know L, right? So all these are numbers. All these are numbers. The only thing that I don't know from these equations is omega squared. And it turns out that there are particular values of omega squared that actually work out so that the left-hand side gives you 0, so it matches the right-hand side, which is 0. You understand what I'm saying? That's what an eigenvalue problem is. Now, how do I find the eigenvalues of the system? Pretend all these are numbers. All these are numbers. All these are numbers, except for omega squared. How do I find the eigenvalues of the system? I find the determinant, and then I can now find the eigenvalues of the system. That's one approach, doing it by hand, right? The second approach is go to Mathematica and go to MATLAB and enter these matrices and let Mathematica and MATLAB give you those eigenvalues, right? That's the approach that you could use. But now, remember, right now, at this point in time, I have not imposed the boundary conditions yet. I want to do that. I want to impose essential boundary conditions. It's clamped free. Remember, it's clamped free in this example. Okay. By the way, I'm sorry. I should skip a step. I should skip a step. So this is the element formulation for any element. This is true for any element E. Okay. So if I have more than one element, what I can do now is assemble the system together. Okay. I can assemble a system together like we've discussed before using the element connectivity metrics. Okay. You understand how to do that? Excellent. I can do that here too. It's not difficult. I'll have For every element, I'll have an element connectivity, and then I'll use the element connectivity to assemble the system together. Okay, so I'll do that. But what I want to do really is let's go to a single element. I don't want to do two elements because that sounds appealing for a homework problem. So we'll do one element. Okay, I actually did 20. In the example problem I'll give you, I did 20. So if I give you 2, I hope you're not upset. Okay? Isn't that fair? Isn't it fair I'm doing one element here and 20 and I'm giving you 2 for homework? Is that fair? It's unfair. But it's also fair. Okay? Goes both ways. Okay. So I have a clamp system, single element. And for single element that's clamped, so presume now that I assemble it all together. Just presume that for a second. So if I assemble it all together and it's clamped, then degrees of freedom 1, V1 and theta 1 are 0. You agree? So then the first two equations are not really relevant to what I'm trying to do anymore, and I can reduce the system into just the last two equations. Okay? And when I look at the last two equations, this is much more tractable. Do you agree? This is much more tractable. And I can actually do this by hand now because I have all these numbers. And when I find the determinant, what I will find is a quadratic equation, which you can actually solve by hand. Okay? That determinant is going to give you a characteristic equation on omega squared, which you can actually now solve for. When you do that, okay, when I use these values of E, A, L, I, and rho, okay, when I use those values and I plug it in here, okay, I'll be honest with you, I did not do it by hand. So I went to Mathematica and actually got the numbers out. Okay, that's what I did. I encourage you, it's my opinion, that if you've never done it, it's worth doing it once by hand. That's all I ask you. I'm not asking you to do the homework by hand. I'm asking you to do an example by hand. So look up an example online. Okay, that's easy. Do it by hand, and learn how to do it if you've never done it, so you can gain the experience. After you do it once, just use Mathematica and MATLAB after that. You don't have to keep doing it. Okay. But I think once in a while, even I do it, so I can remember how to do it for myself, my own sake. Okay. All right. So when I did that in Mathematica, I'm being fully honest with you. That's what I used. I found omega squared to be equal to 2.56 10 to the 5. And so frequency is basically square root of that divided by 2 pi and get 81 hertz. And omega squared is 2.49 10 to the 7th, and the frequency is 794 hertz. Now, I want to point out a few things here. How many eigenvalues did I found in this system right now? 2. Was there infinite amount of them?
If you had more nodes.
I didn't get infinite number of eigenvalues, right? Did I? I only had 2. Can I produce more out of this? No, that's all I got. How many degrees of freedom I have here? There are 3. 2. How many eigenvalues I got? 2. That's interesting. In a continuous system, how many degrees of freedom I have? Infinite. How many eigenvalues I have there? Infinite. How many eigenshapes I have there? Mode shapes. Infinite. So here, because I reduced the system to a discretized system, now I'm going to have as many eigenvalues and eigenshapes as I have degrees of freedom in the system. Okay? And not only that, I have found the eigenvalues. Now that I know the eigenvalues, anybody knows how to get the mode shapes that go with them? What do I do? Eigenvector, how do I find them? Sorry? No, by hand. How do I do that? Thank you very much. All I do is take this 2.56 10 to the 5, I plug it in here, and now I have a 2 by 2. And since I have a 2 by 2 times V2 theta 2, what I need to do is solve V2 in terms of theta 2. And when I do that, now I can normalize it to get unity, the vector is unity, or I can normalize it against something else. But don't you agree that amplitude is somewhat arbitrary at that point? That vector is arbitrary in nature? Yeah? Okay. So let me show you what I did. So I actually plugged it in, 2.56 10 to the 5. And then when you solve V2 in terms of theta 2, and you normalize it to 1, the eigenvector you get is actually 0.998, 0.069. And I repeated the process with the second eigenvalue. Remember I had two eigenvalues? Yeah? So for the second eigenvalue, I plugged it back in here, and I got this as the eigenvector. Now, what does this eigenvector mean at all? Do they have any physical meaning? Yes, they do have physical meaning, and they actually represent the shape that single element is going to take. Okay? And I did that. I actually went back and plotted it. So I took n bold times vector number 1. Eigenvector number 1. This is 0 and 0, remember? V1 is 0, theta 1 is 0. Yes? Isn't this what I got for the vector? For the first vector? Yeah? Isn't the shape functions times this displacement going to give me the shape, the displacements of that? Yeah? Okay. So then I'm going to call this phi1 bold on purpose. I'll discuss why I'm calling this phi1 bold. But I want to remind you that phi1 bold is a vector. In this case is 4 by 1. If I plotted this and I did it in Mathematica, what you get is that this is a shape. Okay, that's the first shape. That's the first bending shape. That's actually the first mode shape, and it's actually the first bending mode of that beam. Can you imagine? I want you to think about this. I have a clamped beam. It's clamped, the beam. Is there a more fundamental shape than that you can draw up? Can you think something more fundamental than that? No, that is the fundamental shape of this beam. That is the simplest shape you can take in a free vibration problem. You follow?
So how frequencies apply to the beam?
We will cover that. Right now, there's no frequencies applied to the beam. We're trying to understand the DNA, the dynamic characteristics of that structure. In this case, a beam. We're trying to understand how this beam will deform is in its fundamental shapes. What are the shapes this beam can take? Okay, that's what we're talking about. So the second shape they can take, because I have only could calculate two eigenvalues, is this one. So I actually plotted shape function times the deflections, okay, and what I got was this shape. Okay, that's the shape I get. Okay, two of them. Now when I compare this, some observations before I continue comparing things and doing things. Observations. We have 2 degrees of freedom, so we have 2 eigenvalues, which are eigenfrequencies. We can call them eigenfrequencies because the eigenvalues happen to be the eigenfrequencies, or the frequencies. We got 2 corresponding eigenmodes. You agree for each frequency I had a mode, a shape? Yeah? So let's call that mode shape, or eigenmodes. That's another word that's used, another term. A system, generally a system with n degrees of freedom, will have n eigenfrequencies and a corresponding number of eigenvalues, n of them. Okay. In a continuous system, as we discussed, I will have infinite number of eigenfrequencies and mode shapes. Another observation is that the eigenshapes in these plots, do you agree that they're arbitrary in amplitude? If I wanted to say, okay, if I said this is my eigenmode, I could say that multiplied by 2. I could scale it by unity, so that I'm basically scaling to unity value. Don't you agree that I can scale it to whatever I want because these are eigenshapes? Yeah. Okay, so I can scale them.
So you see some characteristics, right? And does that mean this beam cannot have other shape than these 2?
It could have, but these are the ones I could calculate with the way I did it, right? Because I only have 2 degrees of freedom, I could only calculate these 2.
When
Sorry?
When given frequencies of 794 and 80.
So this frequency is a frequency at which this beam is vibrating. Okay? That's the shape that's taken at that frequency.
So it's not frequency from outside.
No.
That
So
shape-
this frequency is not the frequency of the excitation frequency. It's not the force frequency.
Yeah.
It's the dynamic characteristic. It's the characteristics of the structure. The structure has two characteristics, the frequencies and the mode shifts that go along with them. So in the video I showed you, the Tacoma Bridge, video I showed at the beginning, that bridge in its own has some fundamental frequencies and some fundamental shapes. The forcing function that came in, which could have been the wind or some other event, caused particular mode shift to get excited. And that's why that bridge deformed the way it deformed. You follow?
Yeah.
Okay. Excellent. Good question. Please stop me if you have any questions, because this is not a very quick subject to go through. Okay. So I want to point out the eigenmodes have arbitrary amplitude. We don't have an amplitude that there's no single value of amplitude that makes the left-hand side equal to the right-hand side. So you can have different amplitudes of V2 and theta 2, doesn't matter. Okay? As long as the relationship between V2 and theta 2 is fixed, I know how these two are related, the left-hand side will be equal to the right-hand side. As long as this V2 and theta 2 take the values that we calculated here for mode 1 and mode 2. Okay, so let's take a 20 element. So I took 20 elements, okay? That's not very hard to do. I mean, Mathematica actually give it a stiffness matrix. You can actually do, I think the parameter to calculate is eigensystem. That is the word that you will write it down. Eigensystem, then you put the first matrix and the second matrix. And that's going to generate automatically the eigenvalues and the eigenvectors. So you don't have to do much more than that. In MATLAB also has that approach. You can do that. Now, Abacus and many other codes have a frequency extraction procedure. They have a way to calculate these frequencies in mode shapes, and they're using something called Lanczos. LANCZOS is the frequency procedure that these codes are using to extract the frequencies and mode shapes. Okay. So for 20 element system that is clamped, how many degrees of freedom I have? 42. 42 degrees of freedom. And then two of them at the beginning, node number 1, let's call it. Node number 1 is to the very left, let's say. So I have 2 degrees of freedom that are fixed. So therefore, instead of 42, I have 40. You agree? Degrees of freedom. So I should have 40 eigenfrequencies and 40 eigenmodes in this scenario. Okay. So I assembled the stiffness matrix and mass matrix, huge matrix. So me trying to, I tried, but I gave up. So I gave you how it looks like. Because if I do a print screen from Mathematica, it looks too small. So I decided, let me print out some numbers so you can see. But I think visually, it's good to see what's going on, you know. So this is a 40 by 40. I want to point this out, 40 by 40. And that's 40 by 40. Okay. Now, what I should do is give this as a homework problem, so you do it by hand. What about that? I think there will not be very happy people here.
See you in a couple of weeks.
Couple of weeks. That could be a good final exam problem, isn't it? Do it by hand. That's the only problem with the exam. Just do that.
Oh, yeah.
Well, no, it's not a good exam problem at all. But you can see here that given this K stiffness matrix and this mass matrix, given that information, given the density, the area, the modulus, the length, I can now calculate, and what Mathematica just did that for me, I can calculate the frequencies. And so when I look at the frequencies for the two element, I think with this single element, isn't it? Yeah, this is just one element. That's an error. So can you help me account for that? So one element, only 2 modes, and this is the modes I get. The analytical solution gave me 80.2, very nice. The second one is not as good, 506 versus 794. But hey, what if I use 20 elements? Look at that. Between the analytical solution and finite elements. So, in other words, what I'm comparing here, I'm using this formula right here at the bottom. I'm using that formula for a clamped beam. That's what I'm using. And so, when I use that formula, this is what I'm getting analytically, and then this is what I'm getting with finite elements. Now, how many of these can I have? I didn't continue, but how many of them can I have? 40. And for each of these, you agree that I'll get a mode shape that goes with them? Yeah? And so I didn't want to plot the mode shapes because I'll have to do it piecewise. For element 1, I have to. Now, you'll do it in your homework, trust me. With a 2-element problem, you're going to do that. But I will have to plot the mode shape, so I'll get the frequency, right, which is 40 by 1, a 40 by 1 vector. Then I'll have to take all those values and map them out for element by element, right, and plot how it looks like as I move along the beam. Well, that was going to be time consuming, so I didn't do that. But I could have done it. Okay. All right, do you follow? You follow what I'm saying? Yeah? Okay, so why not, let's just jump to abacus then. How to do an abacus, because if I can just use abacus, let abacus plot the mode shapes for me. I know I'm going to match what abacus has anyway, right? My Euler-Bernoulli beam formulation that we discussed here is the same one that abacus has. So we should get the exact same thing. So let abacus plot it for us. Here you define the nodes, but there are 20 of them. So there's 20 of them, 21 of them, and I didn't want to write all of them, so I put 3 dots. But if you want the actual input file, we can make it available to you. For the purpose of fitting everything here, I just kind of truncated that. Element definition, beam section the same as before, material, elastic, density, and then you have the step, and it's as simple as putting a frequency comment, star frequency, and I asked for 50 modes. In reality, I should have asked for 40. I have boundary conditions fixed on the left-hand side, and that's it. That'll be enough, and we'll give you the modes. You see how simple that is? Simple? In fact, it's so simple that it's simple. I cannot make it more simple, because it's simple. All right, so one thing that I added here is called restart, write. I did that because I want to store mode shape and frequency information into this file. It's going to generate a file. It's good to have it. That basically, I call that the DNA of this structure. So that file is going to contain all the modes and all the frequencies. You don't have to use it again. You don't have to calculate this again. If you need to do some random vibration analysis or some transient modal solution, guess where I will go? Do I have to run this again and wait for a couple hours? No. I just did it once, and that's where I'll go. That's my database. I see this frequency analysis, this free vibration problem, I see it as a DNA. It's basically, it defines how that structure is going to behave in its lifetime. It has all the information on how that structure is going to behave. That's the way I view it. So when I plot, go ahead.
How are you able to ask for 50 modes if you only have 40 nodes?
Yeah, that's what I said. As you have just asked for 40. I think I did 50 and it was fine because this Euler-Bernoulli beam has axial flexibility. And so now I have 3 nodes. I have 3 degrees of freedom per node. So I will have about 60, don't quote me on this, but you'll have 63 degrees of freedom. The left-hand side is fixed, so you have 60 degrees of freedom really, because you have axial flexibility. Okay? Our formulation that I just discussed does not have axial flexibility, so we're going to have 40. But yeah, I asked for 50, but I didn't plot all of them. I just focused on the first couple of them. Okay. Now, I plotted them. I went to abacus and plotted shape 1. That's FEA 1 bold. FEA 2 bold looks like this. Doesn't this look similar to what I got earlier? Yeah, that looks very similar. That's the second bending mode. Look at FEA 3 bold. Okay, this here I didn't put FEA bold 4 because it's the axial mode. So I didn't include that. You know, it is a mode. It's a possible mode. But in our formulation, we didn't include that. Right? I could have included it, but I didn't do it. The fourth mode, that's bending mode, is this one. The sixth mode is this. The seventh mode is this. You can see that it's bending more and more. There's more bends every time I go up in frequency. Okay? Yeah? Have you ever seen a board? So have you ever seen a diving board? I mean, if you went to watch the Olympics and you have TiVo or whatever, and you went slow motion, and when the guy or the girl jumps from the diving board, have you ever seen the diving board deform like this? I personally have not seen that. It's possible it's happening, but it's like micro. You have to like really like, I don't know, put laser and measure how it's moving perfectly to get that information. But visually, it looks like it's maybe bending like that and maybe like that. Maybe. Somewhere in between. Maybe this one even. Who knows? Probably there. But you don't see these high modes participating, do you? They probably exist, but they're not showing up as cleanly. You agree? Maybe as the beam starts to settle down, maybe those modes show up, but there's so little amplitude, probably doesn't even show up, right? I put the note here on your question: 60 eigenvalues, 60 mode shapes, 60 of them because of the axial flexibility. Okay, but if we ignore those, we should really have 40 of them. Now, how does that compare to what I got with Mathematica? Look at that. That's abacus, that's us, 5 elements. And it's matching 1 to 1. I expect that. I mean, it should match. And the analytical solution is really good agreement also with abacus. I didn't continue because I didn't want to overdo this, but you get the idea, right? And as I go up in frequencies and mode shapes, you'll start seeing an error showing up. Okay, it won't show up for a long time. It's going to show up like a mode 25 or so. Okay. Any questions so far? Any questions so far? You understand what we're doing here? We're trying to understand the dynamic characteristics of the structure. Yeah?
So for understanding the characteristics, how do you decide to do the clamp beam? Why not the beam?
Well, I mean, I chose clamp beam as example of the class. I could have selected simply supported as example of the class. But why do that when that can be your perfect homework? Or why give you the solution to your homework? Why do that? Why not give you that as a homework right there? You see what I'm saying? I hear you.
You mentioned that there's going to be errors when you go further down the list.
Yeah.
Why is that so?
Well, so for example, when I look at this, I have, how many elements I have here? 20 elements? Yeah? The more bending I have, so the more frequency and bendings I have, my elements are going to perform poorly, right? Because it needs to conform to that shape, and it can't, right? The analytical solution can. The analytical solution can give you very sharp oscillations on that beam, right? But because I have a finite number of elements, I cannot really do that, right? And the same goes with the 2 element. The 2 element I have here, you know, that was the best shape I could do. That's the best shape I could do with 2 elements, and clearly that's off from the analytical solution. I mean, that's not close. That's 794, and that's 506. So 2 elements could not represent the exact mode shape of that of the analytical solution. You got it? Great. So moving forward here, so let's talk about it. So the mode shapes are essential. They're actually very important information. This is very important information in a modal transient solution. So when I'm doing a transient analysis, a time-dependent analysis that's linear in nature, these mode shapes contain valuable information about that structure. And what I'm going to do, I'm going to go to that database of mode shapes and amplitudes. Sorry, I don't have amplitudes, but I have the mode shapes. I know how the shapes should look like. I'm going to pull from them. Okay, I'm going to say, maybe my structure behaves like this mode shape and maybe like this mode shape. Okay. Well, I can't really do that, right? I can't really, for a very general problem, that was very hard to do. For me to, if I put the mode shapes into finite elements, I'd rather just the finite elements tell me which mode shapes participate, which ones don't. I'd rather just leave it to finite elements to do it for me. In a modal transient solution, we will always use the mode shapes to determine the response of the system. That's really what we're trying to do. And we'll use these to define how the structure behaves. In the previous example, each mode shape was 1 by 40. And so in this case, we'll have 40 mode shapes and 40 eigenfrequencies. So if I were to stack a mode shape next to another mode shape, next to another mode shape, how big the matrix will look like then? If a single mode shape is 40 by 1, and I have 40 mode shapes, how big is my mode shape matrix? 40 by 40. That 40 by 40 matrix, my mode shape matrix, contains all the information about, not all of it, it contains up to the information that's relevant for that structure, for that discretization, right? Because in reality, it's not all, because all will mean I need to have infinite, a matrix that's infinite, right? Because there's infinite mode shapes. But because I've discretized the domain, this matrix now contains that DNA we're talking about, that dynamic information of the structure. Okay, I want you to note that all mode shapes are known from the frequency analysis. We know that. We know these values, these phe's, we know them. Okay, this phi 1, phi 2, phi 3. You understand that? Let's go back and revisit two-element example. In the two-element example, you can clearly see here, phi 1 is fully known. I know this. Phi 2 is fully known. Now, phi 1 and phi 2 can be scaled by a factor, by some amplitude. But in general, it's shape, right? Yeah? Everybody got it? Okay, so I'm going to do something that now the excitement begins. No pun intended, because we're looking at excitation frequencies here. Okay, so the excitement begins. Now I'm going to start a new topic. So put a break in your head. I want you to understand right now that what we've done so far is to define the dynamic characteristics of the system. That's what we've done at this point in time. And so moving forward, what I want to discuss is the following. So what if I know these are the mode shapes, you agree? And they go on and on. I'm not showing all 40 of them because it will not fit in this page. But I want you to understand the concept. Phi 1 bolt, phi 2 bolt, phi 3 bolt comprise this deformation. They tell me how these shapes look like. Will you also agree that the amplitudes to this are basically arbitrary, right? But let's say that for each mode shape, I assign an amplitude A1. Not acceleration. This A is not acceleration, it's an amplitude. So for mode shape 2, I'll assign an amplitude of A2. For mode shape 3, I'll assign an amplitude of A3. And so forth. So how many amplitudes will I have? 40. So if I have 40 mode shapes, I will have 40 amplitudes that go along with them. You agree? Yeah? Excellent. So I found these mode shapes from my frequency analysis, and this is the information I have of the structure now. And what I'm going to basically tell you is in a linear transient modal analysis, what we're trying to say here is that the deflections of the beam upon forcing function, so the deflection of the beam subject to some loading condition to that beam, that deformation is going to be made up by a linear combination of these modes. Isn't that cool? Can I represent the deformation of any beam, okay, of any condition I apply to that beam the deformation of that beam is going to be made up by a linear combination of these mode shapes. Now let me explain to you something. Okay. How many unknowns I have here? 40. Now let's take a wing, aircraft wing. Well, let's take a 1,000,000 degree of freedom, which my colleague in the back works on. Probably, right? Sometimes. All right, but I'm not off, right? Can be millions of degrees of freedom. All right. What if I calculate the frequencies and mode shapes of that $1 million degree of freedom system up to the modes that I care about? Say I want to compute them up to 200 hertz, because I think that's what's relevant to the problem, okay? Maybe, you know how many eigenmodes and frequencies I could have? Up to, maybe for that problem, I'm going to make it up for this example. I want to say 200. Maybe it's too much. Maybe 200 is too much. Okay, fine. Now, if I take that same problem and solve it with the techniques we talked about last week, where I discretize the time domain, the way I did it, I'll have to solve a million by million matrix at every time step. But what's amazing about this is that if I took that 1 million degree of freedom system and I calculated the DNA, what I call DNA, the frequencies and mode shapes, up to, say, 100 hertz, because that's what I think is relevant to the problem, and there's only 40 of them, so then if I have 40 mode shapes now that I'm considering, how many amplitudes I have? 40. How many degrees of freedom I have? 40. So I've taken a 1 million degree of freedom system that takes forever to solve, and I've now can do it with 40 amplitudes that I don't know. Do you follow me? You want me to explain one more time?
Yeah.
One more time. Or 2 or 3 more times. So at the end of the class, you can talk to me more too. But what I'm saying is that the deformation of the beam, okay, is going to be comprised by a combination, a linear combination of these mode shapes, right? So if I have 40 mode shapes here, the deflections of this beam will be basically A1 times Phi1, A2 plus Phi2, A3 plus Phi3, etc., right? And so in this particular example, how many amplitudes I have? 40. And I have 40 mode shapes. These are known. We know what the shapes are. We don't know what the amplitudes are. And what I'm saying is that the deflection of the beam can be described with these 40 amplitudes. And what I was trying to show you was the benefit of this approach. The benefit of this approach is that if I have a spacecraft or a wing or a very complicated piece that has millions of degrees of freedom, and I were to calculate how many mode shapes and how many eigenmodes I will have in that system. 1 million, say. How many frequencies I'll have? 1 million, right? But if what is relevant to the problem is only up to 200 hertz. Let's say that what's important to the problem is only up to 200 hertz. I don't care anything above 200 hertz.
Oh, yeah, that was my question. Why do
Then-
you care only 200?
Because maybe the forcing, and I'll discuss this in a few more minutes, but maybe the forcing function you're applying, the frequency content of that is not greater than 200 hertz.
Oh, that's fine.
Maybe that's one reason. Okay? And so, if I take that problem, that 1 million degree of freedom problem, if I only consider things up to 200 hertz, then instead of having million eigenmodes and million amplitudes, I can maybe consider the first, all the ones that go up to 200 hertz, which could be maybe 200 of them. So now instead of solving 1 million degree of freedom times 1 million degree of freedom stiffness and mass matrix and inverting that and using Newmark beta method at every time increment, I've simplified the problem into solving it for less number of degrees of freedom. By way less. I mean, huge number, huge decrease in number of them. Is that clear? Is that clear? What that verbal description is clear. Okay. So that's what I'm talking about here, truncated space. It may be convenient to use less number of modes in a linear dynamic formulation. We call this mode truncation. I can use less of them. The frequency content of the forcing function can be used to determine what modes can be truncated. So again, if I have forcing functions that go only up to 100 hertz, Maybe what I want to do is only go up to 150 hertz. So for example, let's go back to this example. Say that my forcing function is frequency content of that forcing function is not greater than 100 hertz. Are you listening? So how many modes I have that I need to really care about? One. Just one. That's the only one I have to look at. Okay? For this example, this hypothetical example, I may have 40, but maybe just with one I can do a good job. So what I've done now, I've truncated the space, and I'm putting R for reduced. So before I went from A1 up to AN, N it was 40, for the example. Let's call this R, and maybe R now is the first two mode shifts, so R is 2. So now instead of, say for the spacecraft example, 200, there's 200 mode shifts, there's million degrees of freedom, so million mode shifts. Now reduce it to 200 of them, right? So this R is 200 basically. Okay. But phi, the phi, the number of rows there continues to be n because, again, the deflection of that beam, I still have 20 elements. For example, for that beam, I still have 20 elements. You agree? So I still have 40 degrees of freedom. So I'm not changing that. What I'm changing is how many modes I want to include in the solution. You follow me? Yeah?
That's going to still stay at million?
Sorry?
So that's still million by
Yeah,
million?
that's still a million. This vector is still a million degrees of, I still don't know this vector. But what is important though is, what is the only unknown here now? What is computation expensive? It's really finding these amplitudes. But since I'm only finding the first 200, that's a huge reduction in computational time. Don't you agree? Yeah? Okay, so I've truncated the space. There'll be an error. Of course there'll be an error because higher modes could contribute to the behavior, but you're making an assumption. You're making an assumption that the energy content of those higher modes is not significant to the problem of concern up to the modes of interest. There's other ways to account for that. It's called residual modes. You can look at the residual modes, but we won't have time because this is covered in much more advanced structural dynamics course. And actually, I'm going already advanced. So if you have questions, I can direct you to some papers or some books on this. Okay. So, all right. So I want you to focus right now a little bit because it will become a little bit more complicated right now. So these, do you agree that after I discretize the domain, this is what I get? The spatial domain. After I discretize the spatial domain, we already discovered that this is what we get. Everybody agrees? Yeah? Yeah? I mean, this is what we covered last Tuesday. You get a million degree of freedom by a million degree of freedom, million degree of freedom by a million degree of freedom, million degree of freedom by a million degree of freedom. It's huge. Then I have these Newmark beta method on that every time step. You agree? So instead of that, what if I make D a linear combination of these phis? And these phis, you agree that they're known? These are all values? These are all values. I know them. Okay? I know them 100%. But what I don't know here is these A's. And so if I, instead of, for the beam example, if I selected 3 modes instead of 40, then I don't know basically 3 of these coefficients, this A1, A2, A3. And let's make this a function of time because I want them to vary as a function of time. I'm going to put all these phis, by the way, I'm going to put them, all these phis, into phi bold. And I'm going to put these amplitudes into A bold. What is the size of phi bold? If I'm selecting only, let's say for the example problem I'm giving you, for the clamp beam, there's 40 degrees of freedom, and I'm going to select just 3 modes. How big is phi bold? Huh? 40 by 3. So there's 40 degrees of freedom that are unknown. I don't know D, right? There's 40 of them, isn't it? 40, yeah? And so phi 1, phi 2, and phi 3, I'll just select 3 of them. So then this becomes 40 by 3 of them. Phi 1, phi 2, phi 3. Okay? And then A bold becomes 3 by 40 in essence. Sorry, that's wrong. It'll become what? I'm getting confused. 40 by, I'm sorry, there's only 3 of them. A1, A2, and A3. It's a vector, in essence. Okay. Any questions on that? No questions? So let's not freak out. The symbols look very complicated, but they're not complicated. This just contains a DNA. I call this a DNA, this guy right here. That's what I call it. Anytime you see this, this guy contains the dynamic information of that structure. And these are the amplitudes that should go along with them so that structure behaves properly for the problem in hand. If I substitute this V bold here, okay, then I have a mass matrix. In our example, is 40 by 40. You agree? This is 40 by 3, and this is 3 by 1. Okay. So I basically have these guys very well set up. Not bad. Not bad. How many equations I have here, guys? 3. Trick question. Let's try this again. 40 by 40. Phi is 40 rows times 3 columns because I'm using the first 3 modes. So phi 1, phi 2, phi 3. Agree? So far, what's the size of these 2 things together? Huh? 40 by 3. And this is 3 by 1. Oh, you're right. Yeah, you're right. 40 by 1. I'll get to that soon. Okay, so you're right. 40 by 1. So 40 equations. So this is not very helpful yet. But hey, what if I, so this is a trick now. What if I now multiply, pre-multiply everything by phi transpose? Phi transpose. Okay? Let me multiply everything by phi transpose just for fun. And maybe it's not by fun, it's because I'm going to show you something really cool. Phi transpose, phi transpose, phi transpose, phi transpose. Now let's try the example again. Let's try one more time. What is phi transpose now? 3 by 40? Yeah? 40 by 40? 40 by 3? 3 by 1. I get a 3 by 1. I get 3 equations. I went from 40 equations to 3 equations, didn't I? What's more, I want to show you something really cool. Remember K bold and M bold was fully populated with numbers everywhere? Remember that? I'm going to show you. I won't show you here, but you'll show yourself in the homework. That when you do this operation right here, when you do this operation right here, and you do this operation right here, it's going to give you a fully diagonal matrix. All the off diagonals will be 0. And you will have 3 uncoupled equations. Fully decoupled from each other. Okay? So I went from a very now let's redo this example with a spacecraft. Million by million, million by million, and we'll have used Newmark method last week to solve this. If I can now use a linear transient model analysis, let's try. So million by million, million by million, huge problem, long time to solve it. Let's say now that for the problem of interest, I'm interested on stuff up to 50 hertz, 75 hertz. For whatever reason, that's what I think I should be using because my forcing functions may not have frequency content beyond them. Maybe in that problem I have 10 degrees. Sorry, in that problem I'll get 10 modes up to 50 hertz, right? I'll get 10 modes up to 10 hertz, and then for frequencies, 10 frequencies, right? So if I can write D bold as a linear combination of 10 modes, so 1, 2, 3, 4, 5, 10 modes, then D bold is 1 million by 1. And then phi bold becomes 1 million by 10. You agree? Yeah? And then you're right. You're right. This equation has a million. There's million equations here. You're right. But when I do phi transpose, now I'm back to 10 times a million, million times a million, million times 10. So I get 10 equations. I went from million to 10 equations. You see what I'm saying? What is the only unknown here, by the way? I want you to pay attention. What is the only unknown? A. A. I know phi, remember, I know the shape because that was a DNA, I calculated that before. I know the DNA of the system. Okay, so I do have 10 equations. And what's more is that, and I basically covered this already by talking to you, but it results in our equations, reduced number equations are, so in the spacecraft example 10, in the beam example 3, in the way I did it, like the hypotheticals. And what's more is that these eigenvectors, or mode shapes, are orthogonal to the mass matrix, which is orthogonal. This is basically going to give you a diagonal matrix. So if you take two modes, any two modes, and you did this calculation against the mass, you'll get 0. It's insane. All the diagonal terms will be 0. If you did it against the stiffness, all the diagonal terms will be 0. But the diagonal terms will be a single value, and this one will be a single value. Okay. What's more incredible is if I take the ratio of Ki divided by Mi, you know what I get? I'm going to get the omega I squared, which are actually the fundamental I recovered the DNA of the system somehow. But I don't want you to memorize that fact. That's fine for now, for you to understand this at this point. So in essence, I went from this equation to fully decouple. Each of these equations is separate from the other. So for each amplitude, I have one equation, and they're decoupled from each other. Fully decoupled from each other. Any questions on this? So the magic is happening here. This operation, when you do it, is going to give you a fully diagonal matrix. It's a property, okay? And if you're interested in derivation, where that comes from, we can, after the lecture, we can derive it. But for now, right, it's a finite element course, not a dynamic course, so I want to make sure we're focused on finite elements. But you guys understand what we've done? For the spacecraft problem, we went from million degree of freedom by million degree of freedom, you understand? To down to, in the example we gave, how many modes I selected for the spacecraft? At 10. So I went to 10. I'm now 10 here. Fully decoupled. Fully decoupled. Okay. So let me cover a little bit about damping here. So how you calculate these guys. So typically these guys, it's basically Ci equals 2Ci omega I Mi. You know the mass, you know the frequency for that particular row. And so you can measure Ci. That can be measured. That's called the damping ratio. Okay. Typically you can assume it to be 1%. So if you have that, since you can basically plug in here in the diagonal terms, all off diagonals 0, just plug in here this value in that diagonal. Okay. This is a set of uncoupled second-order differential equations which you can solve for A. And if I know A now, you agree that I can get A from here as a function of time? Yeah? Yes? So if I know A and I know the phis, don't I know the deflection of that beam or the spacecraft? With just 10 equations, in this hypothetical example, I'm able to describe the behavior of a million degree of freedom by a million degree of freedom system. By tracking the amplitudes that go along these mode shapes. By finding what these amplitudes are that go along these mode shapes. Do you understand the revelation here? Or You want me to go over it one more time? Okay. You also have the video lectures which you can replay. And if not, you have Leonardo or myself to talk to after the class. Now, I don't want you to get confused. You know, right now I showed you the fundamentals, but now we have to discuss the initial conditions. You still need to figure out what the initial conditions are. The initial conditions are known in the original system. I know them in D, right? I don't know them in this new A. I don't know what this A mean. They're the amplitude of these mode shapes, but I have to relate the initial conditions to these guys in some way.
So your amplitudes are a function of time, right?
Yeah.
So you still have to convert it multiple times in order to find the amplitude of each instance of time, right?
No, because this is a single equation. They have, for the spacecraft example, I have only 10 equations here, and they're fully decoupled. There's nothing to really invert here, you just solve it. There's no matrix to invert, right? It's a single equation. Remember, maybe in mechanical vibrations, maybe, if you've seen it, you have a single mass with a spring, right? And you have to solve that differential equation? Yeah? That's it. I reduce a very complicated system into 10 decoupled equations. 10 of them. Okay? Yes? It's fully decoupled now. I went from million equations that have to invert, fully coupled, to 10 of them for the spacecraft example, 3 for the beam. 3 equations fully decoupled. Basically a mass, a spring, a dashpot. That's it. That's what you're solving. That's it. And if I find these A's, these amplitudes for each I, then I can now get the full description of the deflection as a function of time. What's more is that we're not done yet. We now, so the excitement has ended. Now we have to figure out how to describe the initial conditions. How we come up with these initial conditions. So the initial conditions can be found. So if I have dt is this. You agree? We covered that. So dt is a linear combination of these mode shapes with these amplitudes. They are unknown, basically, that I'm trying to find. What I can do, I can pre-multiply this matrix by, or this equation by phi, so mode shape S, times the matrix bold M. And if I do that, okay, do you agree that we already said that if this index and this index are, if this, basically, if this shape and that shape is a different one, that should go to 0, remember? Yeah? We already said that. So we basically said two different mode shapes, when you put it through this calculation, should give you 0. We already covered that. So all this will be 0, right? Except for one. So the only one that's not going to be 0 is the one that has phi s here, basically. One of them will have phi s, and that's going to be not 0. So basically, I end up with this equation. And now I can solve for AT in this manner. Okay, these are all known. I know the mode shape. You know the mode shape. You know the mass. And you know the initial condition. So I'll cover that. But you know this. You know all these values here. And then for velocity, just put dot there. Put dot there. Put dot there, and then you have that. So to get the initial conditions, then yeah, that's it. You know, d sub 0 gives you a0, and d dot at 0 gives you a dot at 0. So now you have the initial conditions. Now goes back, guys. It goes back to just elementary spring, mass, dashpot, fixed, oscillating mass. So if I know the initial conditions for velocity, displacement, now all I have to do is calculate how that vibrates, and I get the amplitude A. If I get the amplitude A, what do I get? From the mode shapes, isn't this amplitude the multiplying factor to the mode shape? So I get the displacements as a function of time. A little bit more on damping. Systems in general do exhibit some amount of damping, and that needs to be accounted for in some way. You don't have to account it for if you want to be super conservative, but most likely you will have damping in the system, and 1% is a good assumption to start with. Typically, damping is every material has some damping because the material itself could have internal friction within the material that causes friction within the grains or whatnot. So that's introducing the damping to some level. You could have damping from a dashpot. You put a dashpot there on purpose, and like an isolator on purpose, to damp out those motions, those vibrations. So you'll have damping. There's two approaches that we can use. We can basically impose what the damping should be at that particular frequency, and we cover that here when I was covering this. I know the mass, I know the frequency. I can measure this through experiments, so then I can specify CI on the diagonal. Just put the value right there. No worries. Proportional viscous damping is another approach that people use. In that case, what you do is you make your damping matrix, you make it proportional to mass matrix and stiffness matrix. And abacus has this one and the previous one we just talked about. So abacus actually talks about this too. And you can calculate what A and B is through experiments. So I gave you some equations. I don't want to go through all the math. But the bottom line is that CI, the damping ratio, can be calculated. So A and B can be calculated based on the damping ratio and the frequency. So what you can do is an experiment where at a particular frequency you determine the damping ratio. And so if I do the experiments at two different frequencies, don't you agree that I'll have two equations for A and B? Yeah? You follow what I'm saying? So if I have, at frequency 1, I calculate damping ratio, and then at the second frequency I calculate the damping ratio, I measure it. Then don't I have two equations, and then I have two unknowns on A and B? So I'll find A and B, and if I know A and B, I can plug it in here. But what is cool is that M, all right, this is what's cool. I don't know if I did it here. I didn't do it there, but don't you agree that if I do phi transpose M, phi transpose, I get a diagonal matrix? And if I go phi transpose K, phi transpose, I get a diagonal matrix? Well, that's exactly what I'm saying. So, actually I did it here, didn't realize that, but this becomes diagonal. So your C matrix becomes diagonal automatically, okay? And the CIs are given by these constants here. This, and you know A and B, you know the omega, you know the damping ratios, you know the mass for that row. And so now you know CI, okay? All right, so that's a damping right there. There are some issues with damping. Paper from 2016 has found that this approach here, right there, has some significant concerns because it's non-physical, but has been used in practice. Okay, so I'll let you read this paper. You can get this paper through your library and then make your judgment. But I think this paper makes very good points about being fundamentally flawed. But it is used in practice in every book. Maybe every book will get rewritten because of this paper. So I will let you know that you should read this paper if you're in dynamics, if you work in this area. And actually, he's my boss's boss, so I know him. Right. So what is the analysis process flow? What is the analysis process flow? So in general, you develop the finite element formulation for one element based on the partial differential equation. Then you assemble the system of equations with the connectivity matrix. You impose the essential boundary conditions. And then you determine the mode shapes and frequencies of the system. We call this the free vibration problem. That right there is a DNA. This is what I call the DNA step. This was telling you how the system is going to vibrate, okay? And at what frequency. The total deflection of the system is assumed to be a linear, so we're going to assume that the total deflection of the system as a function of time is a linear combination of these mode shapes, okay? And we can use a truncated set of mode shapes to actually get the solution to the problem. And from here, I showed you that I can develop an uncoupled system of equations. They're basically a mass, a dashpot, and a spring. And I can impose the initial conditions to solve this. And I can solve them using the Newmark beta method. I can still use that if I wanted to. And once the solution is obtained, you can go back. If I know the amplitudes, I know the mode shapes, I know how the deflections vary over time. You follow the process? So I do have to explain one more thing, how to apply Newmark beta method when you have damping. So when you have damping, you're going to have to solve this equation at t plus delta t. Now remember, everything is uncoupled now, so you don't have to, this is not a mass matrix now. That's just a single value here, just m. Small c, small k. These are single values. But the process is similar. And for u dot, you're going to substitute this equation here. And when you work through all of that, the final equation that should be used to solve for acceleration is this one. And this is augmented now for the damping. Okay. Go ahead.
So that both M is not a matrix?
So now, so remember, we uncoupled. We went from a coupled system to fully uncoupled. Everything's uncoupled. Just values: mass, damping, stiffness. And what's more incredible to me, and I think I may have missed it. I may not have covered it. What's more incredible to me, if I take the ratio of Ki divided by Mi, that ratio, Ki divided by Mi, I get the frequencies, I get back the DNA of the system. That's what's amazing about this. Okay, so I went in, benefits. Let me just summarize the benefits. So we have uncoupled equations of motion instead of having to solve a fully coupled system of equations where the reduced set R could be 10 and N could be 1,000,000. I reduced it. Now the assumption there is a linear combination of these modes, so it works very well for linear systems. But it's also used for, some people do use it for nonlinear systems, but you have to be cautious and you have to understand what you're missing there, right? All right, so how do we do this in abacus? In abacus, what you will do, remember when I had a restart step, I was writing the solution to a file? I was writing the DNA. Remember that step in abacus earlier? Yes? So now I'm going to read that DNA. I'm telling abacus, I know the DNA of this structure, so please read it for me. That's what that step is doing. It's reading the information, the DNA. And then you will, in this example, what I wanted to do is I wanted to apply a load slowly. I want to increase the load slowly, 100T. So distributed load 100T on the 20 elements. And what I wanted to do is at 0.1 seconds, I wanted to let it go, the load. I want to remove the load. I was thinking maybe that's what's happening when a diver is kind of like pushing down. I mean, it's probably less seconds, but it's just an example, so you can see what happens. So don't you agree that when the diver leaves the board, now there's no load applied? You agree? Now, this is wrong because I applied it, I think I applied it as distributed load. It's clearly a concentrated load, maybe towards the end of the diving board. But the point here was to show you how I did it. I put the amplitude. Here is a step definition. Here's the modal dynamic solution. So if you put start modal dynamic, that's going to initiate this transient modal analysis we're talking about. It's going to do this decoupling we're talking about. It's going to do all these steps for you, plus Newmark beta and all that. And so I'm solving every 1e minus 5. I can do that, and it runs really quick because, again, these are all decoupled. Okay. I selected how many eigenmodes I want to include. Remember, we talked about I can include as many as I want. Yeah? Are you with me? I'm truncating the modes. I'm teaching you that I can do it. Abacus allows me to do that because it's true. This is real life. So instead of including 1 million for a spacecraft, or for the beam was 40 of them, right? 60? I'm saying just use the first 10. Because, you know, I truly don't believe that this beam is going to deform with all those waves in dramatic fashion. I really don't think that's going to happen. Because I feel the frequency content of the problem that we're looking at is really not like this, okay? I put modal damping of 1%, okay? And I just wanted to know the accelerations and velocities. So you guys can see here, I select a truncated set. That's what initiates the modal dynamic. I'm getting the DNA of the system. And now, oh, this is how you do the restart. You have to read this file. So you have to do abacus, job name, and then restart equals the file name. That has the dynamic, the DNA contents of the structure.
What is that, 10?
Sorry? Oh, I'm applying a modal damping of 1% for modes between 1 and 10. Remember, for each mode, I could have a different damping, right? I said that for each frequency, I can measure the damping. I'm going to assume there's 1% for all the modes in this example. It's a good assumption, 1%. That's a starting point. And so now, this is the mid-node deflection here. This is the deflection of the tip. In this example, I'm not letting it damp out. And then here is a video I'll be showing you. I went to Abacus and exported the animation of this. So you guys can see, oh. Sorry? What's that? What if I want to use a Windows Media Player instead? Okay, can you guys see? Okay, you can see here I'm slowly applying that load. It actually gets boring because I don't know why I went so slow here. I exported every single frame. I'm applying the load. Keep applying the load. I'll tell you when. About 0.1 seconds. Just wait until 0.1 seconds. You can sleep a little bit. I'll wake you up. I keep applying that load. I just keep applying it. I, of course, exaggerate the deformation a little bit so you can see what will happen. Okay, about 0.1 seconds, very soon I'm going to release it. I'm going to let the load go suddenly. Okay, I want you to focus on the shape that it's taking. I want you to focus on the shape that it's taking. I think you can see the first mode there. And I think at one point in time, I think I saw the second mode too. I don't know if you saw it, but it was kind of there. You see what I'm saying? Do you see the third or fourth mode there? I don't see the 10th mode there. I don't see the whole thing going, right? Yeah? But I included it anyway. And guess what the amplitude for that mode was? Close to 0, right? It didn't select that. Basically, the amplitude was about 0 for that one. Okay. And then you will see the motion kind of dying out because I put 1% damping. Okay. All right. I find it very, very interesting because this shows you exactly what I'm talking about. It shows you that not all the DNA, right? The DNA, when I applied this forcing function, which was a person or a load being released, that the frequencies that came to light are the first bending mode, and I'm not done yet, by the way. But you can leave if you need to leave and watch the video at home. I have more to do here. So let's talk about a spacecraft here. That's a spacecraft. Here is a reference for that picture. This is a finite element spacecraft that has look to me, I couldn't tell from the images, but you can see very small elements there. This looks like million degrees of freedom, but just to give it a benefit of doubt, let's say it's I think it's a million. It's calling a million. So some of the frequencies was 16 hertz, 17 hertz, 65 hertz. Some of the motions were different, like torsion. There's bending. You can see that's bending right there. The spacecraft here has over thousands of degrees of freedom. And in this paper, they actually determined all the modes below 100 hertz because they felt that in actual application, the spacecraft will not see, they don't expect forcing functions with frequency contents greater than 100 hertz. That's what they felt, and they talked about. So the dynamic characteristics here, these values were checked against tests. They actually did some testing on the spacecraft, and they vibrated the structure they have accelerometers to basically verify the models. I'll talk about that in a couple of minutes. So you can simulate the dynamic response, transient response, like what we did on Tuesday, but that would mean I will have to invert million degrees of freedom by million degrees of freedom and solve for every time step as a function of time. Or what I can do is get the mode shapes, and here there was maybe 10 of them. I forget, the paper described them. Maybe there's like 20 of them, say. And because I have 20 of them, how many unknowns I have then? 20. As a function of time, I have to find. Instead of a million as a function of time, I have 20 of them. Isn't that computationally finished? Oh, one more thing. They're all decoupled. I don't have to invert anything. And so you can see the strength of this approach right there. These models can be, what good does it do if the model that you constructed, the finite element you constructed, is not good? It's modeled incorrectly. You have things that are not done properly. That's why we do something called modal testing. And this is done in civil engineering and spacecraft and aircraft, so all the disciplines do it. Modal testing. I showed you an example of a spacecraft. I'll show you an example of a civil engineering type structure. Modal testing allows identification of the natural frequencies and mode shapes of the structure, so the actual ones from the test. So you will usually use a dedicated modal test equipment. You'll basically put accelerometers on the structure. That's going to measure, it's going to basically give you the mode shape information, the thing that we're looking for. And it's going to give you frequency information as well. And it actually can give you damping information as well through the impedance. With this information, you can now verify your model. And you wonder, how can I verify my model with this test? Well, somebody came up with this clever approach, because remember we talked about the mode shape. When I multiply the transpose of the mode shape times the mass matrix times the mode shape, what should I get? Huh? Diagonal. Okay. So let's say the mode shape of the test. Say that finite element model was perfect like the test. What do you think is going to happen when I take the mode shape from the test, transpose it, times the mass matrix, transpose it, but now I multiply against the finite element mode shapes? I should get 1 if it's perfect. If the test is equal to finite elements, I should get 1. So if I take the mode shape from finite elements, and I'm missing a transpose here, and I multiply by the mass matrix, and I take the mass matrix multiplied by the phi of the test, my goal, this is called the cross-orthogonality check. If this check gives me diagonals of 1 everywhere and off diagonals of 0, you know what? I have a finite element I can trust for modal analysis, for transient modal analysis. Here's an example of a structure. I got it from this paper. But they actually put accelerometers everywhere, and they actually compared the analysis. Let me continue, and we can talk at the end. And then they actually plotted the mode shapes with finite elements. They got the frequencies, and they measured them through accelerometers. And then they compared with the calculated ones from finite elements, and they compared so well. Look at that. The mode shapes also continue to show very good correlation all the way to 12 modes. Not too bad. But that's the frequencies. What about the mode shapes? So again, you want to make sure that this calculation gives you as close as 1 as possible in the diagonal terms, off diagonal terms, 0. But that's in practice very difficult to do because no finite element model is perfect. So what normally you have is a criteria for good correlation. So good correlation, we're looking at diagonal terms greater than 0.9 and off diagonal terms less than 0.1. Frequencies, you want them to be between 3 to 5% within that. But some requirements are more strict than that, much more strict than this. It just depends on the program that you may be working on. Okay. Here is an example of a cross correlation that was done on a spacecraft. This comes from this paper here. So I gave you the reference if you want to read that paper. You should be able to understand all these papers now with this knowledge. And you can see here the frequencies between finite elements and test was very close, 4% off. Here was 6% off. It actually validated their criteria. The criteria is 5%. And then also you have the cross orthogonality check, the one we talked about, phi transpose and phi. You know, we know if it was finite elements, you agree that if this was finite elements here, that I should get one diagonal? Yeah? So it makes sense that this check is a good one. So if I do cross orthogonality between FE and test, you can see that the diagonals were close to 1 for the most part. And there's almost no error after 30 modes here. Mode number 30 over there starts to show some problems. Okay, not too bad. Okay, and at that point you're above 50 hertz. Probably in this project they probably didn't care more than 50 hertz. I can't remember from reading the paper, but you guys can go back and read that. No model is perfect, is my point. Here is an example that I was going to have Leonardo do. So what I'm going to do is so first of all, thank you for listening for 2 hours. So we'll stop at this point right now. However,
All right. So to conduct it, extraction of the frequencies from this from a model, we're gonna import this model from any CAD. So we go to the menu, to the bar menu. We go to import. We go to part. Once we go to part, we need to find the file and just click to import it. In this case, the file is in millimeters, so we're gonna multiply by some scale to make it in meters. So let's apply the scale. Just yes, it's okay. Oh, strong.
It just crashed.
Yeah. Okay, let me do it again.
Nothing's perfect in real life.
Okay, let me repeat again. We go to File, Import, Part. Let's select the part we want to import. Just leave it like that for now. Here it is. I think some factor for the scale is affecting the program. So just keep it like that. We're going to follow the same procedure we already are familiar with. So the part is already created. Let's move to the property. Let's create some material property. This time, we need to be careful to assign some mass to the part. So go to general density. Let's assume that this is a 7,800 units for the mass. Now go to mechanical, tab elasticity, elastic. Let's apply a Young's modulus, 0.07 e to the 9, and 2.33. Okay. Once the material is assigned, we need to create a section. In this case, the section is going to be solid homogeneous for this problem. The material is already selected, so we don't need to select the material. Just OK. The section is created. Now we need to assign the section to the part. So for this purpose, we need to select the entire part. Once it's selected, we assign the section we already created. The section is assigned. Let's move to the next step. We're going to create an instance for this part. This time it's going to be independent instance. So we are meshed on the instance. Let's select OK. Let's create the step. This is a crucial step we need to carry out. So to create the step, this time, let's call this frec for frequency step, right? This time is not we're going to select for the procedure type a linear perturbation. And for linear perturbation, we're going to select frequency. Once we select frequency, here in this slot, we're going to select the numbers of eigenvalues we want to solve for. Okay? So let's say we can, since it's a solid model, there is so many eigenvalues. This time, this just did 5. Okay? Once we do that, you can remember what Professor said earlier. This is the eigensolver for abacus. Here it is, but it's already selected, so we are not modifying anything. So once this step is created, the next step should be apply a load, right? But for the load, we are not applying any external load. So it's a free vibration. We can constrain the model Um, do you want me to constrain the model or the rigid body?
Let's go for it. No, constraint.
Constraint. So we're going to constrain the model. The model is going to be constrained at the crankshaft pin.
Actually, let's do it on constraint.
No constraint.
Yeah, so they can see the free body modes.
So we're not going to constrain the model. So it's going to be the rigid body
So,
mode shapes.
so we need to get more frequencies, not just 5.
Yeah, I need to get back.
Same.
Mhm. So let me get back to the step. We're going to modify the step for more frequencies. 15. And once it's done, just get back to the menu, to the module. So we don't have to do anything in the module section. So go to the mesh. This case, we're going to select a tetrahedron element shape. The technique to mesh is going to be free. Let's go to assign an element type to verify. So we're going to select a standard quadratic in the family 3D stress tetrahedron, and we're going to use a modified formulation. Just to improve, we're going to set a second order accuracy for this model. It's just some modification in the element type. So the element type is the one you can see at the bottom here. So it's a 10-node modified quadratic tetrahedron. This is the element we're going to use. So once it's selected, let's mesh the entire part. So here's the connecting rod mesh with the text. It's quadratic text elements. All right, so what is next? Next is just create a job. Let's create a job. We name the job as a Frex job 2. It's going to be saved in the temp file, in the temp folder, and just continue. Once we continue, we don't need to modify any of the selected features in this window. So just OK, and we can start to submit the job. So it's running. The first step is done. We're waiting for completing the second step. Since we are calculating 15 mode shapes, it's going to take some time. It's not.
Can you open the message file so they can see what it looks like? It's a message file. MSG.
Yeah. We have some warning, but no, we don't have errors so far, so I think it's fine.
Yeah, that's fine. Just do the message.
Message file?
Yeah, it's showing the file. It's a nice solver. If you look through, you can scroll down so you can see. It shows a number of equations, the degrees of freedom. I think it finished too.
Yeah. So the analysis is completed. So let's see the results. So to see the results, at the bottom, you can read each of the frequencies and the mode shapes. So for the displacement, the first mode shape for this rigid body motion is this. The second one, you need.
Can you simulate it? So you can simulate it on the left-hand side, the animation bar.
In the animation bar,
So go to the left. Where's the mouse? Okay, move to the left. Go down. Go down.
you mean this?
No. Here, click on this.
Oh, okay.
see how it's moving.
Okay.
Slow down the time.
Yeah, that's a rigid body because it's not constrained, so there'll be 6 of them. So explain that in the video.
So what we're doing is making a video with all of the 15 mode shapes that we already selected. So basically, since this is a rigid body motion bar, it's not constrained at any of at any part, so it's free to move in the space. And the 50 mode shapes are there.
You do result step frame. Go up where it says result step frame. Pull that up. It's literally easier to see than here.
Oh yeah.
You can click any of them. You can see the first 6 are 0, basically. So 6 degrees of freedom.
So by looking to the step frame, we can select any of the eigen, the frequencies, any of the mode shapes, and see what is that. This is the second one. This is the third one. Fourth one. Fifth one. And so on.
That's a real one. That's a real one. That's bending.
So we can see here some bending in this mode shape. So other bending, right?
Keep going. That's the second bending mode. You said for the video, second bending mode.
This is the second bending mode. This is extension.
Axial, looks like axial motion.
Yeah, like actual deformation.
There's a torsional mode.
This is a torsional mode. So it's just one more mode shape left. This is the last one we select. Okay. All right. So this is how you can extract the frequencies for your solid model and extract the mode shapes. So all the information are here. You already saw how to animate. You can do it from the toolbox area, or you just can go to the menu toolbar and select harmonic. Both ways you will get it.
You can create a video.
And you can create a video and export it if you want to do it. Okay. So I think I end the presentation at this point. Thank you so much.